righty. Let's go ahead and get started. Welcome. Thank you all for coming today to the Fibre Channel Generation 8 update. Whoops. There we go. First, I want to thank the SNIA community for providing the opportunity for us to be able to come and talk to you all, the 200 corporations, the 2,500 active members, as well as the 5,000 worldwide IT users and professionals. So once again, thanks to SNIA for this opportunity. And best of all, thank you to you guys for coming and participating at the SDC 2024 here in Santa Clara. Today, we're going to go through the features of the Gen 8 Fibre Channel. I'm going to highlight a few things, certainly the speed and a couple of automation characteristics that are part of the Gen 8 specification, just to give you an idea of where Fibre Channel is. Before we wrap things up, we will end the summary with a little peek into what's going to happen next. Mark did a fantastic job of giving us a preview of this, so I hope to go into a little bit more detail on a few things that Mark touched on during his presentation. First of all, I'd like to chat a little bit about how the process works within the Fibre Channel community. Currently, there are two organizations. There's the Fibre Channel Industry Association, which Mark talked to you about just a few minutes ago, which is really the marketing arm of the Fibre Channel community. And then there's the Insights T11 Standards Organization, which is the group that provides the technical input into the standards and then develops those standards. We work under the umbrella of the International Committee for Information Technology and Standards, which really is a large group that provides the administrative services necessary to produce standards. Ultimately, the standards take the input from the end users, of course. Marketing and needs requirements are evaluated by the Fibre Channel Industry Association. And then we get innovations and both for Fibre Channel and storage that are inputs by the membership into the Fibre Channel Committee. Those are sorted out into the various standards definitions, which are then produced and published by ANSI. In some instances, our standards will be promoted also to the ISO level for an international organization standard. So that's the process that we go through. So let's take a moment now and look at what we did for 128 gig. Mark showed this particular historical representation of where Fibre Channel began way back in 1988. Some of you probably even recognize some of the work that was done in those early days. Craig, I'm looking at you. Yeah. Notice that arbitrated loop and then fabric services were some of the very first feature sets that are put into the standards. As we worked our way up through that first decade and got to 2 gig, we then started working on not only faster speeds, but virtualization via the endport ID virtualization that is done at the physical Fibre Channel port, and then broke into converged networks for FCOE, a Fibre Channel over Ethernet solution. The next decade, we got involved into the NVMe over fabrics, of which there are several implementations already available today from all the major storage vendors. And now we're more focused on automation within the SAN. And we'll touch on a few of those features, such as fabric notifications, as well as our investment into the management of NVMe in a Fibre Channel network. Topping it all off was the 128 gig specification, which was completed in late 23 and published in 24. To get kind of a better view of what the 128 gig specification focused on, this is a little bit different chart describing not only the different speed throughputs that are shown at each one of the speed bumps here, but also the encoding schema. And you'll note here at the break between 32 gig and 64 gig, the encoding changed. And that was fairly significant for the Fibre Channel industry and as well as the transmission industry in general. Our ability to achieve the higher baud rates was requiring a more effective encoding schema, which is referred to as PAM4. Also to note on this particular slide is the roughly every 4 years, there's a new generation of fiber channel that is provided with the expectation of future speeds coming out, the specifications coming out in 2025, 29, and then 33 as we look way out into the future beyond 256 gig and into 512 and terabit speeds. Fibre Channel has focused largely on a handful of very specific requirements for its standard specifications. First of all, of course, is the throughput, enabling to double the speed or the throughput at each generation of Fibre Channel. Secondly is the bit error rate that we're focused on, which is 1 to the minus 15. Those two components provide probably the most significant challenges with each iteration of the specification. Certainly then there's backward compatibility, and the Fibre Channel industry has always kept a N-2 characteristic with regard to our ability to plug into existing equipment. So that's key to being able to provide customers with an upgrade path that they can utilize as they migrate their systems forward. Distance has always been a key focus of the Fibre Channel solutions, both on multi-mode fiber and single-mode fiber. For multi-mode, we have been trying to make sure that we can get at least 100-meter reach each time we generate a new generation of Fibre Channel, and 10-kilometer reach with single-mode fiber. So that particular component, along with the bit error rate that we're trying to achieve, present the technological challenges that the physical interface expert group has to deal with each generation. And then finally, we want to be able to have components that we build to be backwards compatible so that existing components can plug into them. That is, we can take a 128 gig optic and plug it into a link that's connected to a 64 gig or a 32 gig device. Talking a little bit about the modulation or the encoding schema, the bit encoding schema, we made that jump at between 32 gig and 64 gig, where we went from NRZ, which is a single bit representation based upon the energy level that's being transmitted, versus a 2-bit representation. This is what would allow us to actually run the link at a slower baud rate, but achieve double the throughput by encoding these things. So for example, you have 128 gig, which is modulated at actually 56.1 gigabits per second, but is producing a 112.2 data rate. And that is because of the way that the encoding schema works, where different levels of energy represent different bit encodings. And again, this represents a key jump at 64 gig. I'll call it a key technological innovation that was adopted by not just Fibre Channel, but a large amount of the transmission community. In addition to being able to transmit data very quickly, at the higher speeds it becomes much more difficult to do that reliably. So forward error correcting technology was added into the specification. This began actually at 16 gig as an optional function, and then was required at 32, 64, and definitely at 128. Each time we go through one of these generations, we have to come up with a better forward error correcting technology in order to achieve the data rate and the bit error rate capabilities that we want at the speeds that we're attempting to produce for the industry. With 128 gig, we're using a Reed-Solomon block code. You can see here it's 5,140 bit streams that are divided up into 15 symbols. And then spread across those symbols are the error correcting mechanisms so that we can then correct errors across each one of those symbols. You can see at the bottom of the chart where we've advanced. 16 gig, it was, and I forget the name of the mechanism that you used. It wasn't Reed-Solomon. But the bit stream was a 2112-bit stream and a single symbol at 2080 characters. But you can see that at 32 gig, we move up in the number of symbols that we're able to correct. And then at 64 gig, we make yet another step. 64 and 128 use the same technique, but a different interleaving, if you will. And that's a mechanism that provides us with the opportunity to be able to determine the more enhanced forward error correction methodology. In order to be able to bring the link up, one of the other things that is done is at the training level. So when the two sides of the link first come up, we're actually going to run at a slower baud rate. And that allows us to bring the link up from link speed negotiation through optical bring up, and then in transmission training, and then finally mission mode, which is the link is finally up. But at a lower rate, the two sides can actually link up a little bit more quickly and more reliably, and they can determine then at which speeds that they support. And so that gets transmitted between the two endpoints to say, yes, I support 128, 64, or 32, or the other side may say, I only support 64, 32, and 16. They'll negotiate as to which speed that they can come up with, and then they'll bring the link up to full data rate following that negotiation. There's some mechanisms within that transmission marker that allows the two sides to be able to communicate that information, and there's a mechanism that shows, hey, we've gone through this speed negotiation and now we're done, and then we can bring the link to full mission speed. So those are a few idiosyncrasies that are associated with the development of the 128 gig standard. Now you can see where a lot of the technology and I'd say the intellectual focus has been for the team when they're building these things. From a standards perspective, we hit our milestones. PI8 was completed in October of 22 and accepted in October of 23. Basically, what you can glean out of that, those two milestones is that the Fibre Channel community comes to completion at a certain point and then sends it out for public review. The public has the opportunity to make comments, and then once those comments are complete and incorporated into the standard, we send it to through the finalization process for publication by ANSI. So the final step is, I'll call it more of an administrative thing. Typically, our partners or the Fibre Channel community can start building products once the standard is complete from the Fibre Channel community. So we could actually start building toward delivering products back in October of 22. The framing and signaling standard is another component that goes with the physical interface standard. Those two standards typically progress together. The physical interfaces is basically defining exactly what's on the wire, whereas the framing and signaling describes how to interpret the things that are on the wire. Finally, I want to point out that the physical interface PI9 project has been approved, and we're already working on that. And that work actually started, as you can see, basically 2 months after we completed the 128 gig specification. Now, switching gears a little bit from the physical layers piece to more of the logical or the protocol layer piece, one of the components that was built with the Gen8 specification is a function that we refer to as fabric notifications. So to set this up, to give you guys an idea of what's going on here, is we had a lot of customer input from that first slide where I showed how the standardization process worked. At the top end was the user level input. We had inputs from customers who said, hey, I buy a lot of Fibre Channel. I build these SAN A, SAN B type arrangements with an air gap in between them, but I've run into this particular problem. And that problem is that in this air gap situation, they would sometimes have a sick but not dead path. So a path that was working well enough for data to be able to be transmitted across it, but not well enough for it to be done efficiently. What was happening at the logical layer is that the multipath solutions could not tell that they were running into a physical problem versus a logical problem. So those software components were actually using software techniques to drive information across the lines to try to figure it out. While they're doing that, they're preventing activity from their alternate path. And typically what was happening especially like in a database environment where you're going to read the record first, make a modification to it, and then write it, that read wasn't completing, so it would completely time out. And that would actually drop the performance of this AB SAN that was supposed to be highly resilient to near zero. Completely frustrating for SAN administrators, and certainly frustrating for CIOs who are saying, hey, I'm paying a lot for 2 times the infrastructure to get half the performance. So in order to solve that particular problem, which we found is usually associated with either marginal cables, SFPs, or various other connector type issues. That is, that the interfaces along these paths were working well enough for things to happen, but not well enough for sustained I/O. The other thing that was benefiting the fiber channel industry as well as when we brought these, dealing with this solution, is a lot of the components in this system had matured to the point where they have the ability to detect these kinds of things. But they were really surfacing them out to their individual components. So for example, if the array could detect that its receiver was bad, it would send a notification to the storage administrator. If the switch could detect that its transmitter or receiver was bad, it would send a notification to the SAN administrator. If the storage could detect that its was bad, the server, he was sending it to the server administrator. So none of this stuff was correlated. And when you got the engineering teams together to try to figure out what's going on in a highly tense environment, let's say, they were all saying, it's your fault. So the solution was to come up with a mechanism that would allow the system, that is the fabric and all of its participating components, to surface that information to the place that it made sense. In this example, we have a multipath solution in the servers who know precisely how many alternative paths they have. So if we could say, hey, this link between this switch and this storage device is bad, let's send that notification up to the multipath solution, who then says, I'll just take that path and I'll say he's marginal for the moment. I'm not going to use him. I can use the alternative paths. And when the multipath solutions could do that, we found that they were able to restore their overall performance of the system to nearly 100%. And that's largely because they were able to precisely identify that they had a physical path problem and not a logical path problem. And that was what was unique with the development of the fiber channel notifications, fabric notifications functionality. There are 2 mechanisms that were designed as part of that architecture. The first one was I'll call it a software mechanism, and the second one was a hardware mechanism. The notifications use ELSs, or extended link services, to send these notifications up, and then the hardware between 2 endpoints can actually send a character across to each other to say, hey, there's a problem here. We began this study and the development of this standard back in December of 18. It was fully specified in April of 22, and we had the standards complete here in June of 24. And that means all 3 of these standards, framing and signaling, link services, and switch fabric, were all completed here as of June of 2024. Implementations actually came out in 2020. So we started hitting the market with implementations that utilize the software-based FPIN, which is the Fabric Performance Impact Notification, ELS. So it's a command that's used for either the switch or the HBA to be able to say, hey, I've detected a problem. This is the problem I've detected. This is the reason I'm flagging the error, and this is where it is, and send that back to the end device. Or the signal mechanism, which is a primitive signal that can be sent between the devices. So that allows us to categorize the types of errors into different buckets, if you will. So a link integrity notification can be sent when we see that there's an error on a particular path. That's a physical error, like we've exceeded the number of CRCs detected on a particular port. For congestion or situations, we can also send a notification to the endpoints to indicate, hey, you are behaving in a congesting manner, and to its peers to say, hey, we believe this egress port is congested. So those notifications can also be sent out to help drive the communication through the system. And then finally, if there happens to be a reason for the fabric to discard a command frame, we can short circuit the timeout that's set up at the OS level or higher that says, hey, we're going to wait 30 seconds or 60 seconds for a command to timeout. Instead, we can send a delivery notification that says, hey, we know this is not being delivered back to the originator, and then short circuit that process. All of these techniques were designed largely to focus on two things. One, simplicity, and then two, key information. Get it back to the components that know how to manage these types of problems. That is, get it up to the OS. So as you can see, there's quite a bit of work that had to be done. Even though the Fibre Channel community has this messaging, excuse me, that's easy for me to say, messaging system, we needed a way to incorporate that with the further up the stack, that is, from the HBA on up through the OS layers, up to the multipath layers to be able to make intelligent decisions. And that required work throughout the, not only just the Fibre Channel community and ecosystem, but also with a lot of the peripheral partners to help utilize these mechanisms. Let's see. Yeah, this is just an example of the congestion signals notification. In the case of the congestion signals, it's between two endpoints. And the way it's working is that the transmitter is detecting that there are a lot of frames built up behind it and that the receiver needs to receive them. So he'll send a character that gets through the congestion to say, hey, I need you to make a change in behavior in order to consume all of these frames that I've backed up for you. So that's fabric notifications. The other component that's part of Gen 8 is that we wanted to focus a little bit on how to improve our capabilities within the NVMe solution. So the FC-NVMe was originally done in 2014. NVMe 2 came out with a sequence level error recovery mechanism. And then currently we're working on NVMe 3. What I'm talking about here is a management of the NVMe qualified names, which is a way to identify the endpoints in an NVMe environment. Within Fibre Channel, there are two, with NVMe over Fibre Channel, you end up with two components that are really controlling the access control. The first component is the standard Fibre Channel stuff, which is which ports can talk to who. And we identify that at the worldwide name level. So every port has a unique worldwide name, and then those WWNs are collected together in a zone that says these WWNs are allowed to talk to each other. That's great. However, in the NVMe space, there's yet another layer of access control, which are the NQNs. The NQNs are required in order for a connection to be established. So you need a host and subsystem NQN required to establish that connection. And they have to know who's allowed to talk to each other. If you don't get those two pieces together, then we start to have trouble. And that's kind of what I'm outlining here. You can see at the top, we have the connection request that has the two NQNs in it, the subsystem NQN and the host NQN. And then we also have the zoning information. And if those aren't aligned, that is, I don't zone a particular port with who's the owner of or has the appropriate NQN sitting up behind it, I can't create that connection request because the fabric, once it gets down to the Fibre Channel layer, is going to deny that request. So administrators were struggling a little bit on being able to define both. That is, they wanted to be able to see both. So because the NQNs are opaque to the FC connection, it became difficult for the SAN administrator to see that. And the solution really is, let's just have them register that information. So we provide a management system, or server, I should say, that we refer to as the upper layer object server. And you can register a ULP name. And for NVMe, the ULP name is simply an NQN. And then this NVMe, FC-NVMe-3 specification simply says NVMe ports should register their NQNs. So that provides us with a mechanism for registering that information, providing an association by worldwide name. That is, each port can then be associated with the NQNs that you can see behind it. And then that information can be presented to the SAN administrator who can then set up his zoning and his access control on the, at the NVMe level in such a way that they all line up. And then finally, we have a few miscellaneous items that we're revving up for the next generation. Certainly 256 gig follows the exact same schema that we had for 128 gig. We're going to double the speed. We're going to maintain our bit error rate. We're going to look for backwards compatibility with 128 and 64 gig. And then the distance objectives are still the same. We want to be able to get 100 meters with OM4, OM5 cabling infrastructure, 10 kilometers with single mode, and then we want to be able to have the connectors that operate at 256 gig to also be backwards compatible with the other connectors. The space to watch is the 100 meter requirement for multi-mode. This is where things are really, really interesting. There's a lot of work being done, not just in the Fibre Channel community, but also in the IEEE community on the ability to get 200 gig anything, much less 256 gig Fibre Channel, working at that level, and then able to maintain the reach requirements that we want. We're looking at various types of technology. We've recently been able to, one of the ecosystem partners within the Fibre Channel community demonstrated that we can get out to 30 meters with existing VCSEL type technology on OM4, OM5 cabling. That's a good sign. It's not as far as we want. We're certainly hoping that we can get farther, but that's where the research is at this point in time. There's also other techniques that have been looked at in order to achieve that 100 meter reach, such as BiDi, using both the two little fibers inside the cable to go both directions, basically kind of a parallel in both directions. That requires more componentry in the optics, so there's a trade-off there. So there's a lot of work going on in that space, and I'm personally optimistic that somebody's going to come up with a solution for our customers. The other things that we're working on is the ability to identify the enclosure of a Fibre Channel entity. So today we can identify the port with a port worldwide name. We can identify a node behind that port with a node worldwide name. And now with the platform name identifier, that is, I'll call it an enclosure worldwide name that provides a hierarchical level. And this is key for administrators and management automation to be able to understand what that hierarchy is, especially in virtualized environments, and to be able to tell, hey, this enclosure contains this set of ports and that enclosure contains that set of ports, and that they're separate entities and not single entities. Port notifications is an extension of fabric notifications that provides effectively a safe switching type of operation. It's the idea here is that it's a signaling mechanism, again, like fabric notifications are, to allow the system to be able to tell the devices that are affected when a particular port is going to go out of service. So there would be an end user or automation initiated event that's going to take a port out of service, and a signal is sent to say, hey, is it okay to take that port out of service? And then things like an MPIO system can come back and say, yeah, that's no problem, because I can move the workload from where I am to an alternate path, and then you can take that port out of service without interrupting existing operations. This is especially important in mainframe environments. I believe that it'll also affect open system environments as well, providing a higher level of automation for systems. Virtual machine identification is another component that's being worked upon within the Fibre Channel community to help identify particular flows. So behind a single Fibre Channel port, now that you can do 128 gig worth of bandwidth, you can virtualize that rather intensely and have a lot of applications that are using that single port. But when you start to have overuse issues or congestion issues competing with resources, it's hard to identify which VM or virtual entity behind that port is responsible for that issue. The virtual machine identification functions provide us that visibility, whether it's a new header, optional header component that tags each one of those based upon the VM, or it's a priority tagging schema that overloads the priority field in the Fibre Channel header to identify those particular VMs. Then finally, security. Mark touched quite a bit on that in his presentation, but effectively what Fibre Channel is doing is providing an end-to-end secure channel mechanism that allow the endpoints to automatically negotiate the authentication as well as the encryption characteristics between them without having to have a third-party tool deployed in the environment to make that happen. This mechanism, I see this as being an opportunity for Fibre Channel to make it pretty much plug and play when it comes to security. And hopefully that plays well with the enterprise customers who are going to be faced with a lot of the governmental requirements that are coming up in the next 5 years. Finally, I wanted to thank the Fibre Channel Industry Association as chair of the Fibre Channel Standards Committee. I really appreciate the work that the FCIA does for us. We have been around for 25 plus years, actually 30 years. And so it's been exciting to be part of this industry. A couple of the highlights there, 142 million plus ports shipped. You have bigger numbers since then, since I made that slide, so we're doing well. So thank you for attending today's session. I'd just like to point out, hey, we talked about the Fibre Channel Generation 8, 128 gig. Includes not only the speed bump, but the reliability characteristics and improvement of the ecosystem with fabric notifications, a lot of flexibility in the ability to manage NQNs in the environment. And then we've got a tremendous future with Generation 9 already underway with 256 gig, security for the CNSA 2.0 world ahead, and more on integration automation as we move forward. So still a lot of work and exciting things being done in the Fibre Channel community. Thank you all, and then be sure to take a moment and rate the session. Thanks for joining us today.